In this example problem, we have a problem. We have a car that drives around on a flat curve of radius 5 meters. So what we're dealing with is a curved path. And then we have a 5-meter radius. And the coefficient of static friction is 0.45 between the road and the tires. So as soon as we see a coefficient of static friction, it's a pretty good bet that we need the sum forces here. And we want to know what the maximum velocity the car can have and safely make the curve. So we want to have the scenario here where essentially the force of friction static maximum is equal to the net force. We don't want the net force to be too large due to the velocity squared here, that it overcomes the maximum force due to static friction. Then you end up in the kinetic friction range and now you're sliding. Alright, so we need to go through our summing the forces process. So step 1 is to pick an object. So we're going to pick the car. And the forces acting on it, we're going to have a force due to gravity in the negative y direction, a force normal in the positive y direction, and then a frictional force in the radial direction. And then step 3, we want to draw a free body diagram. So we have force normal up, we have force to gravity down, and then we have the radial force, the force due to friction, static, acting in the positive radial direction. Now it's really hard to sort of with the free body diagrams visualize this, where you have to vision, if the car is right here, sort of the force normal and force of gravity are going in and out of the page appropriately, where the radial force is, or the force due to friction, static, is pointing towards the point of rotation. And so as the vehicle moves, y direction is still up and down into the page or out of the page, but the radial force is going to move, so it always points towards the rotation point. So it's not like the x direction, where it's like the fixed direction that the car is going. Alright, so step 4 is to write the Newton's laws. And so you see here I've already written the one for the radial direction. And I got this relationship here by saying that the force normal minus the force of gravity is equal to mass times acceleration in the y, but recognizing this is 0, so you end up with force normal equals, or not equals yet, minus the force of gravity equals 0, and then I added the force of gravity to the other side to get this relationship up here. Alright, so you'll notice we're missing the mass, so it's really hard to just directly plug in here. So what I've done here is I've written down my force of friction static is equal, because remember we want to find the maximum here, so we want to set it equal. And then I have subbed in the force normal, as we've established here, is equal to the force of gravity. So I have subbed that in. And remember, the force due to gravity equals mass times the gravitational field strength, so I did that substitution. And from over here, we know that force in the radial direction equals mass times acceleration in the radial direction. And acceleration in the radial direction is velocity squared over the radius. So I've made that substitution over here. And this allows me then to cancel out the masses on both sides, which allows me to end up with a relationship that tells us that the mass actually doesn't matter. The velocity and the size of the curve is what matters. Now that I have a relationship without mass that I can plug into, I plug in the radius, I plug in the coefficient of friction, and I plug in the gravitational field strength. And this allows me to solve and find that the velocity is equal to 4.7 meters per second.